Now, since this converges,
it's monotone increasing.
yeah, it's monotone increasing. That is true. It's not necessary. Just know that it's a convergent real sequence means that it's Cauchy. So the partial sums constitute a the limit of this thing is the Cauchy limit of these partial sums. And since the series converges, the Cauchy sequence here for sufficiently large index, the difference between A and 2 is arbitrarily small, namely less than epsilon. We would like that to happen. So we can go out and find the n of epsilon that makes this less than epsilon. And once we find that, if both n and m are greater than n of epsilon, then this is less than epsilon, this is equal to this, and this dominates this, which is equal to that. So this sum here is Cauchy, which means it converges uniformly by the uniform convergence test that we just established in the prior theorem. We have now shown that the sequence of partial sums of the absolute values of the Fn of x's is a Cauchy sequence. It's applicable to use the Cauchy criterion for uniform convergence on the partial sums of the Fn's. That's what we're saying. So it's uniformly convergent. So that's the justification for the Weierstrass M test, which is a good thing to have in your pocket.
Cauchy convergence of anything is fairly small.
Well, in a complete space, Cauchy sequences converge. In an incomplete space, they don't. So you have to be careful about that. In the reals being complete, all Cauchy sequences converge. All these arguments in the rational are false. And you can have big function spaces where you don't have complete secret. That might be a good thing just to talk about. If I have a, say, an interval AB compact set, and I have a function f, you guys know that the set of functions that take, well, I could write any set up here into the reals. Any set, but in particular, I'm talking about this compact interval AB. So this is a typical member of the set of real functions from the closed interval AB into the reals. That set with the definitions of f plus g of x equals f of x plus g of x. And constant c times f of x is c times f of x. This is my vector addition and this is my scalar multiplication. The field is R. So what shall we call this thing? I'll just call it A. The set of those functions and the field of scalars, AR, is a vector space. Okay? Prove to yourself, it's not terribly difficult. This scheme satisfies all the vector space axioms. This is my definition of vector addition. This is my definition of scalar multiplication. The reals of the scalar field, the vectors are these functions that are, this is a typical. Okay. I can define the norm between two functions to be the supremum for x in AB of absolute f minus g. Thanks. So in other words, if I have g is some other function here, then I look at the supremum, it looks like it's happening over here. The supremum, the difference between those two, maximal supremum of that, right, is the norm. If this is a compact set and these guys are continuous, this is certainly a vector space. What if I restricted it to just the continuous ones? Certainly a constant times continuous is continuous, and sum of two continuous is continuous, right? So the continuous functions would be a subspace of all functions, right? And if these are continuous guys here, the extreme value theorem, which I put on our chart there, the extreme value theorem says that the range of those functions is also compact, which means you would attain the max and min, right? You attain the max and min on both these, so you attain the max and min on both of the difference. So the supremum is actually attained here. In other words, the norm of these two functions can be identified with a point where the separation is exactly that norm, right? In other words, there's a point, and there's an x somewhere, well, it'll probably be over here. There's an x somewhere where the difference between f and g, according to this vector space, is represented. It's actually attained. Okay, so this is also called the uniform form. And if you have sequences in this space that converge according to the uniform form, then the convergence is uniform. Okay? That's what's called the uniform form. Or symmetry. Okay. This is the way the distance between any two functions is defined. And since it's a vector space and we have a distance, it's a norm. You can express convergence. You can say that the sequence of functions fn, say, converges to f in this norm if this is true. The limit as n goes to infinity, 0, right? You can couch this also to, given any epsilon, you can make the norm difference less than epsilon for a suitably high n, which is nothing but this, a more technical statement of this fact.
You're saying that kind of convergence is uniform?
Yeah, if you converge according to this norm, convergence is uniform. You can converge point-wise, there's nothing wrong with that. But then you just measure the real distance, point by point. If you do happen to have convergence according to this norm, then you automatically have uniform convergence. That's why it's also called, in addition to the sup norm, it's called the uniform norm. And together, the vector space with the uniform norm is a Banach space. Let's see, it's at least a norm vector space. It should be complete. So it's a, we can show that it's complete. So it's a Banach space. It's a complete norm vector space. Why would it be complete? Well, if you have a Cauchy sequence of these things, then at each x, you have a Cauchy sequence of reals. The reals are complete, so you will find a limit function, right? If you have a Cauchy sequence of these, things, group them along here. They don't all have to be below. There can be some above, right? I'm just drawing them up. What I'm saying, for a particular x, this is a sequence of real numbers, which would be Cauchy because of the Cauchy condition on the entire functions, right? So for each individual x, you have a Cauchy sequence that certainly converges in the reals. So this limit function up here is always there. So these spaces are complete. This is also sometimes written with a little infinity sign here. And then when you talk about Lebesgue integration, where you throw out sets of measure 0, You call this the essential supremum. It means it's the supremum on all sets except sets of measure zero. You throw out all sets of measure zero. You know, the function can be really poorly behaved. The difference could be huge, but if that happens on a set of measure zero, you can throw that out. And the essential supremum is the one that is the one occurring on all sets except those. This is just a little culture.